So far, every limit we have looked at has been a two-sided limit. And what that means is we're looking at both the left and the right to come up with that limit number. Some functions don't even get that. If we just look at our basic square root of x here, that's our parent function. If I wanted to find the limit as this function goes to 0, well, there's no left side to that function at all. So talking about the limit as that function goes to 0 can only happen on the right side. Other functions that we've seen have jump discontinuity. So we can talk about left and right limits even though altogether the two-sided limit doesn't exist. So the purpose of this section is just to look at those one-sided limits, how to deal with functions who have only one kind of limit, whether it's left or right, or they have both a left and a right, but they don't match. So when we start talking about limits from the left, we use a little negative sign there to talk about, hey, we're looking at the value c, but we're coming at it from the left side. If I want to look at the limit from the right, we use a little plus sign in the limit notation to say, hey, we're looking at this function on the right-hand side, from the right scaling to the left. So when we're taking a look at the example here, evaluate each limit, we have a really ugly function, but that's no big deal because it's already graphed for us. So if I want to look at the limit as x goes to 2 from the left, that little minus sign means I'm starting on the left and scanning this way. Well, that limit is -1. Again, the limit is what y value does this function approach as x approaches 2 from the left. The other one, this little plus symbol here, is talking about scanning from the right and getting closer and closer and closer to that value. So as x approaches 2 from the right, the function value is +1. So these two limits don't match, and we didn't expect them to looking at the graph. The graph has a jump discontinuity. So a two-sided limit would not exist, but both of these one-sided limits do. This function didn't shoot off to infinity anywhere. We do get two answers here, a left answer and a right answer. They don't match, so there's no two-sided limit, but you can still find one-sided limits, and one-sided limits can still be useful. Some of our functions, like I mentioned earlier, only have one-sided limits. They don't even get the two-sided one. So we'll take a look at a few more examples. So I have already put these into my calculator. Number 1 is F1, number 2 is F2, number 3 is F3. Just as a heads up, in case you want to pause the video and follow along here, remember inside that smiley face menu, this is where both the piecewise defined functions live, as well as absolute value functions, and fractions if you want to get them there as well. So that menu has a lot of stuff for us. All right, so I'm going to add a graph, and we'll go from here. So I don't even need a table. This one is pretty clear to see. From the left, we've got this piece of the function here, and it stops. Again, they wanted us to find the limit as x approached 3. So we're talking about this x value. So that break there, that jump in the graph, is exactly what we want to be looking at. So if we scroll over to the right, take a look at that y-axis. As x approaches 3, -3, from the left, this graph, the y values, will approach -2. Oop, not Desmos, graphing calculator. From the right, switch over to green here. From the right, now we're talking about as x goes from 2 to 1 to 0 to -1 to -2, all the way out to -3. Now we're looking from the right-hand side. Well, the y value is no longer -2. Now this y value is going to approach -1, 2, 3, 4, 5, 6, 7. So when you have a nice clear graph like this one here, you don't need to bring up the table to get those values. You certainly could if you wanted. Remember Control T. Control T is our hotkey for bringing up a table. Of course, then you would have to go ahead and set that table to being ask instead of auto. So it would be a bit more work to do it this way. 2.997, we actually wanted that to be negative, and then a negative 2.998, and then a negative 2.999, to see that on the right-hand side, this graph does approach negative 7. If you can avoid the table, I recommend doing it because it is a bit cumbersome. The graph here is just fine. For example 2 here, now they want the left and right limit as x approaches 0. Again, both from the left and the right. So I'll use the same colors as last time. We'll let that yellow be from the left. So now note that this function is a parabola here on the left-hand side. As x gets closer and closer and closer to 0, y gets big and then goes back to being small and stops right here. So as x gets close to 0 from the left, this function will approach the value 1. Then on the right-hand side is just linear, so this function is going to continue down, down, down until it stops right before 0 there. So this function is going to approach the value negative 1, 2, 3, 4, 5. Again, you could pull up a table to confirm, but this graph is pretty clear, so we don't need to worry about a table there. Let's take a look at one more example here on Desmos, on the calculator, and then we'll do a couple on Desmos. So for example 3, I want to look as x goes to negative 2, again, both from the left and from the right. So that's the third one that we have graphed here, and this is another one of these functions with a nice jump. So we'll go ahead and use the same color convention as last time. From the left, we have this nice constant function all the way up until negative 2, and that's where we want to check that limit. So when x is getting closer and closer and closer to negative 2, this function is going to approach negative 1, 2, 3, 4, 5. And then swinging back and looking at this function from the right, we get another nice constant function. Of course, now it's all positive numbers. And as we get closer to negative 2 for my x value, this function is going to approach positive 1, 2, 3, 4, 5 as a y value. So as we take a look at all of these different values, note that none of these functions were continuous at the x value that I cared about. However, left and right limits still exist. They don't always match like we see here, but those left and right limits can still exist, and we can still work with them depending on what the problem's asking us to do. Let's switch gears a little bit. For the second set of 3, I'm going to jump over to Desmos instead of the calculator. So for this first rational function here, I want to look as x goes to 1, both from the left and from the right. So let's go ahead and start from the left. So I already have the function graphed, it's in green. And then I also have x equals 1, the x value we want to get close to, I have that graphed as well. So note that as this function gets closer and closer and closer to that value for x equals 1, it shoots off to positive infinity. And then on the other side, as we get closer and closer and closer to 1 from the right-hand side, this one shoots off to negative infinity. So it is possible for left and right limits to not be numbers. We saw an example of this in the previous section as well. Looking at those unbounded limits, meaning they shoot off to positive or negative infinity. That can happen. Let's take a look at the next one. And the next one I want to look as x goes to 4. Again, both from the left and the right. And so here again, we already have it graphed. And I already have my x value set. Again, I like to have that x equal to the value just so I can see what the function is doing as it gets close to that number. Once again, we can see this function shooting off to positive and negative infinity, but in the other order. Now on the left-hand side, as x gets close to negative 4, y goes off to negative infinity. And on the right-hand side, shooting off to positive infinity. So same idea as the previous example, but now my left limit is negative and my right limit is positive. So a bit of a flip-flop there. And we'll take a look at one last example, everybody's favorite kind of example, trig. We're going to take a look at our secant function as x goes to pi over 2, both from the left and the right. If you remember the trig unit, you're probably expecting an asymptote there. And here we've got it, a nice pretty purple secant function. Once again, looking on the left, as our graph approaches negative pi over 2 from the left, it's shooting down to negative infinity, and on the right, shooting up to positive. So even with trig, we can still look at left and right limits. They still might be infinity, just depends on what's given. I'll go ahead and finish this guy out. And suddenly recognizing that I didn't want that negative sign there. Let's fix it. Ha! Try again. So now if we look on the left, notice that I basically put that asymptote on the other side of the shape. So now my left limit is positive infinity, and my right limit on the right side of that dashed line is going down. Whoops. So this limit is positive infinity, the right limit is negative. Again, it all depends on that x value. For example, if I was looking for the limit as this thing approached, I don't know, maybe 0. If I was looking for the limit as this thing approached 0, then I wouldn't have to worry about this whole left-right business at all. The left limit would be 1, the right limit would be 1, so we would have a limit of 1 as x approached 0. So it really does matter where you are looking for that limit. What x value do we care about? Because that is going to determine whether you have a nice number, whether you have an infinity, whether you get a limit at all, so on and so forth. So do make sure you're looking for the correct x value. Don't pull a Loftus. This video is long enough, so we'll go ahead and pick up two-sided limits in a minute. See you soon.